curvilinear motion is 2D plus. So pretty much anything that's not moving in a straight line, you need at least two variables to describe it. This could be x and y or x, y, z or whatever. Curvilinear motion, you also don't have to use a Cartesian coordinate frame. You could use a polar frame, you could use cylindrical, you could use spherical, you could use normal tangential. We'll get into more of that on Monday. Today we're going to stick to Cartesian, but basically the motion is in two or more dimensions. And so that means that instead of having scalars, now what we have are vectors. So if we go back and look up here, here we had position, velocity, acceleration, and time. All of those were one-dimensional. So now, for curvilinear motion, we have velocity is a vector, acceleration is a vector, and typically instead of S, we use R for curvilinear. So R being the position vector, and it can have X, Y, or X, Y, Z component or whatever. So the relationships are going to be pretty similar, but instead, we have vector signs here. So a vector has a magnitude and a direction. A scalar just has a magnitude. And in rectilinear kinematics, we use S, which was a scalar, because the position, the velocity, and the acceleration were only in one direction. Like there was nowhere else to go. So we didn't need to specify a direction. Now with curvilinear, we have to specify a direction and know like how much is in I hat, how much is in J hat, etc. So that's why we have vector signs here. So that could be a concept question on an exam about the difference between vectors and scalars. So our relationships for curvilinear motion, now we will have V equals dr dt, change in position over change in time. Now, time is always a scalar. Then we have acceleration equals second derivative of r with respect to t equals dv dt equals v dv dr. So pretty much similar, except we swap out s for r and we use vector signs. Okay, so an example of this one, we will do one with Cartesian coordinates. So let's say that we have a bird that wants to fly from Maine, so Maine up at the top of the US over here, and then maybe it wants to fly all the way down to Mexico. For the winter time. So the bird is going to start from here on the ground, and then it's going to launch up in the air and go southwest. So if we put our coordinate frame here and we have X and Y, and then Z up in the air, then this bird will have components of its velocity in X, Y, and in Z. So we'll say given velocity, it looks like it's going in the negative X and the negative Y, and then we'd need to go positive in Z. So we'll just say that V equals negative 3 I hat minus 2 T J hat plus 1 plus e to the negative 3t k hat. and it starts from the origin. So S of 0 equals 0, and I'm going to go ahead and put a 0 vector, so that means 0 in I, j, and k. Oh, except actually this is not S anymore, this is R. Let's see, let's find position at 9 seconds and acceleration at 9 seconds. We will just integrate each piece and take the derivative of each piece instead of having just one equation. So I'll do R and then I'll let y'all do A. Position of t, we're going to be using this relationship right here, v equals dr dt. So integral of v of t dt equals integral of -3 I hat dt minus integral of 2t dt in the j hat plus integral of 1 minus e to the -3t dt in the k hat. So really, we just have 3 integrals to do. So if we integrate -3, we get -3t plus, we'll call this cx for the x direction, I hat, and then minus t squared plus cy in the j hat, and then plus t minus, or really this will be plus 1/3 e to the -3t plus cz in the k hat. So a question in the chat. So let's see, what's the difference between the hats and the arrows? Oh, okay. That's a good question. So the hat is a unit vector. A arrow is a vector, not necessarily a unit vector. So if the vector has a magnitude of 1, basically the one with the arrow has a magnitude and a direction, and the one with the hat on top is just a direction. That's the simple explanation. Now, we know that to put in the initial condition, r of 0 equals 0, then we will have 3 separate equations here. So we will have the x equation, the y equation, and the z equation. So we'll do each one of those separately. For x, we have -3t plus cx, and really this is at 0, so -3 times 0 just goes away, equals 0. So we know that cx equals 0. That's convenient. For the y, we'll have t squared plus cy. Plug in 0 for t, we'll get 0 plus cy equals the initial condition was 0. So anytime someone starts at the origin, it's easy. If it doesn't start at the origin, it's not easy. And then finally, we have the z component. So z, we plug in 0 for all of these. We'll have 0 plus 1/3 plus cz equals 0. Now, in this case, we have cz equals -1/3. So our final equation is r of t equals -3t I hat minus t squared j hat plus t plus 1/3 e to the -3t minus 1/3 for that cz k hat. And now we need to plug in 9 and get a final position. Plugging in the -9 for everything, -27 I hat minus 81 j hat plus 8.67 k hat, and this is going to be in meters, is position at 9. Okay, and so thinking about this, so if the bird launched from Maine and it started flying south, we should have a, or southwest there, we should have a negative x and a negative y, because that would be going in southwest. And then he's going above the ground, so the z component should be positive. So this looks like a reasonable answer. Very good. So we got 0 for the I because derivative of this constant is 0. For the j, we get the -2 because that t reduces exponent. And then for the k, the derivative of the 1 gets 0, and then the -3 comes out in front for that. Now, here we just need to go ahead and plug in 9 for a of t. So we'll say that a of 9. So a of 9 equals nothing in the I. So we can even leave that part out. And we'll just say -2j, which this -2 now is never going to change no matter what t is. And then minus 5.6 times 10 to the -12. Okay. And that is meters per second squared.